Hello everyone, this is Professor Iris Miano giving you what promises to be a rather lengthy lecture video on everything that you need to know for dealing with rational expressions. We're going to reduce them to lowest terms, multiply and divide them, add and subtract them, whether you have common denominators or not. And then at the end, we're going to solve some rational equations. So the very first thing that we'll want to do is define what a rational expression is. It is a ratio, right? Can look like a fraction. And P and Q, as they are presented here in this general definition, are each themselves polynomials, and the Q polynomial cannot be equal to 0. So we're actually going to start by discussing when a rational expression's denominator could equal a 0, and we'll want to capture those values and set them aside or think about them in a certain context later when we solve rational equations. So that's what this next little bit is about, excluding numbers from rational expressions. The denominator cannot be equal to 0, so we want to look at whatever rational expression we're given and focus on the denominator in order to determine which values need to be excluded as possible values that x could take on, okay? So for instance, in this first example, A, look at the denominator of x minus 6 and ask yourself, well, when would x minus 6 be equal to 0? Because that would be a no-go. And what you'll do is create this equation, equating the denominator expression, polynomial, equal to 0, and then solving for it. So that means x would equal 6 in that case. So x equals 6 is going to be the value that's excluded from this rational expression's possible input values. Now this has another context for us later on when we solve rational equations. You'll definitely want to exclude any solutions that would cause the rational expression's denominator to be equal to 0. When those come up in solving them, those are deemed extraneous solutions. We'll talk about that a little bit later. And also when we have rational expressions as functions, when we have rational functions, we'll want to capture those values and set them aside as values that violate the domain. So they are values that are associated with the domain restrictions that come up in rational functions. Anyway, let's have some more examples here and just identifying the numbers that need to be excluded from rational expressions. Here's our next example, B. So yes, there's definitely a numerator polynomial 5x plus 4. We're going to ignore it completely and just focus on the denominator polynomial of x squared minus 3x minus 10. So your first step here, because it's a second degree trinomial, is to factor this denominator, right? Setting it equal to 0. And so here I go factoring it. Sorry, I just kind of like plopped it in there without giving you a chance to factor it yourself maybe. But this is the factored form. And we'll want to solve this factored polynomial equation, in which case we consider the two cases of when this product would be 0. It's called the zero product principle, and that just says give each binomial factor its own equation set equal to 0, solve both simultaneously, and you will have that x equals either 5 or negative 2, in which case the denominator would be equal to 0. So the values of 5 and negative 2 are therefore excluded from this rational expression. Said another way, they are domain violations of this rational expression if it was attached to a function. Okay, great. Another example here, this one's kind of a it's so easy it's hard kind of a thing. Notice that this denominator of just a constant value of 4 contains no variable part, so that means it can never take on a value of 0. So this particular rational expression has no excluded values. If it was a rational function, it wouldn't actually be a quintessential rational function because there's no variable part in the denominator, so it wouldn't have a domain restriction. Okay, great. So then we would, further specify that it's defined for all real numbers. There are no excluded values here. All right, now let's go ahead and switch gears to a different set of examples in which we will be simplifying rational expressions. So this is going to be a lot of basically factoring, canceling out common factors, things of that nature. So here we go. Yep, cancel out common factors. Yes, I'm kind of getting ahead of myself in the thing that I'm saying and what you're seeing on the screen. And also these statements are included in your lecture notes. Yep. Factoring, cancel out common factors, and once all the common factors are eliminated, the rational expression is simplified. Let's go ahead and tackle this first example in this set, example D. So we'll want to notice that the numerator can't be factored, you know, there's nothing to do there, but the denominator can. Let's start by looking at the denominator critically and finding its GCF, also known as greatest common factor. So it looks to me like the greatest common factor there would be a 3y cubed. So pulling that out, the denominator remaining factors become this parenthetical 2y minus 1, okay? And so you can see that there's some stuff that's common among numerator and denominator that can be canceled out. It's essentially the entirety of the GCF of that denominator of through y cubed. So go ahead and cancel those out, right? And it's a good idea to leave a the remaining factor behind when you cancel things out, just to make it abundantly clear that that numerator space does have a remaining factor of 1. It's not just going to disappear or turn into a 0 or anything silly like that. It's going to have a placeholder factor of 1 that needs to stay up there. And the 2y minus 1 that in this previous step where we did the cancellation, having parentheses, those parentheses are no longer serving a purpose, so they can be dropped in order to present your final answer, which is what you see here where my cursor is circling, okay? And that's it. That is as simplified as that rational expression is going to get. Let's move on to the next example. All right, so notice that both numerator and denominator are second degree trinomials, so we'll definitely need to factor them. I'm going to go ahead and bust out a diamond to factor the numerator, in which I populate, you know, the top and bottom diamonds in the way that's always been presented. There's a lecture video on this method going at some length with examples. So if you're looking at this and haven't seen that lecture video, maybe go back and watch the other one so you could be familiar with the diamond method, because I want to go through this relatively quickly because there's a lot of examples in this lecture video as a whole. So these are your initial values. These are the values that complete your diamond. Here I go, splitting the middle term and grouping the terms 2 at a time accordingly. I'm going to find the GCF of each grouping and pull them out, recognize the common binomial factor of x minus 1, pull that out to the front. The remaining binomial factor becomes the 5x minus 1, the leftover bits that are outside the parentheses in the previous step, okay? Now let's factor the denominator with the same process, different diamond here, and then notice that I populate the upper and lower diamonds according to the rule. The upper diamond needs to be the leading coefficient times the constant term, the 3 times -7, right? And then the lower diamond is the coefficient of the middle term, which in this case is 4. Excuse me. All right, so completing the diamond, you will get the values of -3 and 7, which you could, you know, switch their positions if you want to, but this is what I've chose to do. Split the middle term, group the terms accordingly, find the GCF of each grouping, pull out the common binomial factor, and put the other stuff in its own binomial factor. So there you go. So now we can rewrite the rational expression in factored form and see if there's any common binomial factors that we can cancel out. And are there? Yes. X minus 1. The entire binomial factor cancels in numerator and denominator, as you can see, leaving factors of 1 behind that I have like lit up in blue. And then I'm left with 5x minus 1 in the numerator, 3x plus 7 in the denominator. Drop those parentheses because they're not serving any purpose. And that is the simplified form of this original rational expression. Excuse me again. All right. Now here's kind of a tricky one. This is another one of those examples that it's so easy it's hard, but I definitely wanted to formally address this one just because it could come up, and if you need a little bit of trickery to deal with this one, I'm going to show you the trick. Since addition is commutative, we could rewrite the numerator of this rational expression as x plus 5, and then the numerator and denominator are exactly matching, and you can cancel them out as binomial factors outrightedly. So I made this extra step happen where I rewrote it with parentheses on top and bottom, so hopefully it's a little bit clearer that I'm not canceling out the x's and the 5's by any means. I'm canceling out a binomial factor of x plus 5, both in numerator and denominator, and that's what makes it okay to reduce this to 1, which is its actual value. Okay? Cool. So hopefully that makes sense, but if you have any follow-up questions on that one in particular, feel free to ask me in class or in office hours. Send me an email. Ask away in whatever form is, fits you best. All right, here's another weird one that's tricky, okay? Now we have subtraction happening here. Oh, so sorry, I'm getting ahead of myself. Look at that numerator and say to yourself, okay, it's looking a little weird. I don't like that there's no standard format for how these terms are ordered. Usually the variable term is first and the constant term is last, if those are the only two terms in a polynomial. And so just kind of switching their positions is certainly a good thing to do. And it might look as a little bit aesthetically weird because that first term is negative, but don't sweat it. Take out the GCF of -1. And then you'll notice that the binomial factor that remains in the numerator, x minus 5, exactly matches the denominator, which, putting it in parentheses, could be advantageous in effectively canceling out the common binomial factor of x minus 5, which is what you should do next. And then simplify what remains all the way down, and you'll have a value of -1. Okay, so if you have a numerator and denominator who are binomial factors that are separated by subtraction, and then otherwise the two terms exactly match, they're just opposite positions, then you can, maybe bypass some of these intermediate steps and just say, oh, that reduces to a -1. I've seen that structure before, and you can go straight to this result. Okay, cool. Moving on. Here we go. Another instance in which we have a numerator polynomial that's not in the standard form. So we might want to consider taking the, a rewriting of it. In fact, that's exactly what I do in my first step. I rewrite the numerator in standard form, and then I'm setting myself up to factor the denominator because it is a second-degree trinomial. So I'll go ahead and do that. Cool. I also might notice that I have a GCF in the numerator that should be pulled out, and I'm referring to this -3 here, and this will be the remaining binomial that gets left over, x squared minus 1. You might recognize that x squared minus 1 is a difference of squares, and so it could be factored further as an x plus 1, x minus 1. And then, since all of the factoring that's possible in the numerator and denominator have been exhausted, it's the right time to just look at what you have and see if you have any common factors that can get canceled out. And yes, we have x minus 1 and x minus 1 occurring in both numerator and denominator, so cancel them out and then report what you have left. And notice that I have taken this negative sign that was in front of the 3 in the numerator, and I have pulled it out to the so sorry that my voice is getting all grumbly. Let me actually take a moment to pause when I'm done with this problem. You won't notice it in the video. It'll just be like, it'll only take a moment to get a drink of water. But I just wanted to say before I do that, that it's conventional to, if you have a negative sign in front of a string product like we have here and in our final answer, it's conventional to pull it out to the front of the rational expression. Okay, let me go get a quick drink of water. Just a moment. Okay, I'm back. I've had a little bit of water, and I'm hoping that means that I will not be clearing my throat so much in the rest of this lecture video. Here we go. Next example. Let's go ahead and factor everything that we possibly can and see if we can slash. That's basically the name of the game for all these examples. Factor the numerator. The denominator cannot be factored. So the numerator, you'll want to rely on your sum of cubes factorization. which when I think of sum of cubes, I think of this kind of a setup initially in my mind, and you got to fill in the blanks. And what goes in each of these blanks? Well, the first two blanks for the binomial that has a plus sign in between is the cube root of the first term, which is just x, and the cube root of the second term. Cube root of 27 is 3. And then in the trinomial that you have next, the first term is the square of that cube root, so it'll be an x squared in this position. It'll be the product of the two cube roots, so 3 times x, 3x in the middle, and then the square of the last term's cube root, which is the cube root of 27 again was 3, but you got to square it, so 9 will go in this last position as such, okay? So however you have managed to remember the sum of cubes factorization, like do you, this is the way that I remember it. I deal with the signage first, because if it's a sum of cubes, then it's going to be the binomial part has the plus sign in it, and then otherwise in the trinomial it's subtraction and addition respectively in that order from left to right, and then I plug in all of the elements accordingly. I don't know, it's a lot to remember, but that's the way I do it. All right, you might notice at this point that the rational expression in the factored form now has a binomial factor of x plus 3 that occurs both in numerator and denominator. I've added some parentheses on the denominator x plus 3 just to make it super clear that I'm canceling out the entire binomial factors that are occurring here. And then you just report the trinomial that was happening in that numerator as your your final answer, and rest assured that it is prime, because that's something that hopefully you've been alerted to or told or learned when you first learned the sum of cubes factorization, that the trinomial involved in it is prime, the secondary trinomial, which is this guy right here. Okay, moving on to the next example. Remember, the mode is factor, 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 and then cancel out common factors and then report whatever is left. So here's us focusing on the denominator first. We're going to factor by grouping because it is a four-termed polynomial.
Sorry, I'm having trouble hearing you.
Oh my gosh. This is my phone trying to talk to me. Don't be silly. Okay. So, factor by grouping, find the GCF of each grouping, pull them out, recognize you have very much awesomely a common binomial factor of x minus 3, pull it out to the front, the leftover bits get their own binomial. Okay, cool. So the denominator is factored. The numerator, it looks like it has a GCF of 3, so pull that out. And now rewrite that rational expression with everything factored. Do you see anything that could be canceled? Yes, there's a common factor of x squared plus 2, so slash those away, and then drop the parentheses on the x minus 3 because they're not doing anything, and call it good. That's it for that one. Okay, so hopefully that felt good and was relatively straightforward. Yes, and just one more thing. It's because this denominator polynomial had 4 terms in it, that's what prompted me to do the factor by grouping method. Like, there's no other method that I know of off the top of my head that would be more appropriate or even work for factoring that denominator. Okay, moving on. Great. Let's talk multiplying rational expressions. So here's like the general definition of rational expression multiplication. You have 2 rational expressions and you just multiply numerators to numerators, denominators to denominators. If there are common factors that are occurring diagonally across the way neighbors, or from numerator to denominator space at all, you will always want to try and cancel those out before you even do the multiplication, because then you're going to have less complicated things to multiply in the next step. So yeah, we're still going to be factoring as much as we can along the way, if it's possible. Now notice in this first example in this set, example A here, there are no common factors to cancel out, right? You look for diagonally across the way neighbors, or just up and down among each rational expression. There's no simplifying that can be done here. So you simply multiply numerators to numerators, denominators to denominators, and call it good. There's nothing to slash away, right? Okay, now sometimes there will be things to slash away. I'm speaking about this next example B. So here I'm going to go ahead and just kind of extend the division bar for both of those rational expressions and identify that numerators are going to multiply to numerators, denominators to denominators. But if you have the ability to recognize common factors are occurring in numerator space versus denominator space, you slash them away. So here we go. Here's something that I've done that is not necessarily intuitive or necessary. Some folks can slash away just at this stage the way it's currently presented, but if you want to separate all of the factors in such a way that a cancellation will be really satisfying and straightforward, you're going to separate any negative factor as a -1. You're going to separate any variable parts according to known slashes that you're going to make. So what I mean by that is, notice that you have 3 factors of a in the numerator space and then 1 down below. So what I've done here is I took this a to the 3rd power and I separated it into 1 factor of a and then the remaining factors of a, which is a squared. Because I'm going to slash away 1 factor of a up top and down below. So I've separated out what leftover factors of a that I have in order to just be able to easily report what is left after I do all my slashing, okay? And yeah, doing the prime factorization of any composite numbers like I've done with the 15 here, turning it into 3 times 5, that's going to be advantageous for slashing away these 5s. So we've set ourselves up beautifully to be able to do a bunch of slashing, so let's go ahead and slash this up. So the 5 slash away, the 1 factor of a slashes away, the b squareds slash away, because so 2 factors of b occur at least on numerator and denominator, and then you report back whatever's left. What's left? A factor of 2, 2 factors of a up in the numerator. Technically there's a factor of -1 in the numerator as well, but the convention is in your final answer to pull it out into the front of the rational expression, and then yeah, check down below. There are 2 factors of 3 and a factor of b in the denominator, and that's why there's a collective 9b down below. Okay? Does that feel good? Let me know. All right, let's get into some more complicated examples that require some factoring along the way. Okay, so what we've done here is I've just multiplied numerators to numerators, denominators to denominators, and when a particular numerator or denominator contains a binomial factor, make sure you put it in parentheses before you actually implement the multiplication, because you need to multiply the entirety of that binomial or polynomial factor over whatever is going on in the other numerator space or denominator space respectively. Okay? Now, let's go ahead and factor away. Let's factor everything that we possibly can. So not only am I pulling out a GCF of 6 from this numerator binomial factor, I'm also taking that 6 out and in the same step coming up with its prime factorization. Okay, I recognize that in looking at what I've created as the rewriting in this the second step here is not going to result in any canceling out with the 2 and the 3, but it's kind of nice to have that as a rule of thumb anyway. And the remaining binomial factor becomes an x plus 1, and I did the prime factorization of the 14. Down below, I factored the x squared minus 1 binomial factor because it's a difference of squares, and that's its factorization here, these 2 binomial factors in the denominator. Okay. Now we can slash. What can you slash? Well, that binomial factor of x plus 1 occurs in both numerator and denominator, and also a numerical factor of 7. Anything else? Nope. So everything else that's left gets multiplied together. You drop the parentheses for the binomial factor that remains, the single binomial factor that's remaining in the denominator, and call that your final answer. Okay? Great. Next example. Ooh, we got a lot of factoring to do. First step, we're going to smush everything into one rational expression by performing the multiplication, so to speak, but take every single parenthetical piece and factor it away. Like so, and notice that we have a trinomial, second degree trinomial in the numerator, this guy right here, so I'm busting out a diamond in order to factor that. I've got -6 up top, -5 down below. This is what the values that will complete the diamond. Let's split the middle term, factor by grouping, and we're set. Okay, so this is the factored form of this second degree trinomial in the numerator space. Let's replace it with that, factor the GCF here, and do the difference of squares factorization for the 9x squared minus 1. And you will have this. So all of the hard work is done. I know I breezed through that so very quickly. Please, at any time when you're doing this, to convince yourself that you could do it on your own, try and take some pause breaks and do the work yourself. It's good practice, and and really you can choose whether or not you feel like you need to do this practice. I just thought I might remind you that it's a YouTube video, so you can pause it whenever you like. Before I'm about to show you the next step, just to convince yourself that you can do it too. Okay, now it's slashing time, folks. All right, let's go ahead and give this a good slasheroo. Oh, let me give you a little bit of explanation on what happened here. Notice that these two terms are not in the standard ordering. So what I guess I did to get from here to there, right, is I pulled out a factor of -1. I pulled out the otherwise GCF. Well, the GCF, I guess, here was -7x, correct? Which I broke up in the following way, and then I reordered the terms that remain in the standard way, having the variable term first and the constant term second. Okay, so hopefully that makes sense. And one of the really beautiful things about doing that and keeping up that convention is that the resulting binomial factor has a better chance of matching up with something that is occurring in the numerator space. I'm talking about these x minus 2 binomial factors. Okay, but enough talk, let's slash. Okay, x minus 2, bye-bye, 3x plus 1, you're gone. And then everything else that's left, just kind of smush it together. But please do try to refrain from distributing through these factors that you see in front of these parentheses. You want to keep your final answer in factored form, okay? And then also note that there was a -1 factor that got pulled out in the denominator space, just like the -1 factors that have happened in previous examples in the numerator space got pulled out as a negative sign in the front of the rational expression. So should that happen if the -1 factor is in the denominator space. Go ahead and just pull it out in front just to make your final answer look as aesthetically pleasing as possible. All right. Next one. All right, let's divide some rational expressions. It is very much similar to the process that we've just gone over with multiplying rational expressions. You just want to do the keep, flip, change thing, right? The thing you already know how to do in regard to dividing by a fraction. The same rules apply for dividing by rational expressions, because rational expressions are just more complicated looking fractions. So here we go. Let's start by doing keep, flip, change right away. So that's what I've done in this very first step. In, for example, E, I am going to keep the first rational expression exactly as it is presented. I'm going to flip the second one over. So instead of, and then I'll change the operation from division to multiplication. So it'll read as 7x squared over 6 times 2y over x. Instead of dividing by x over 2y, it's equivalent to say that you're multiplying by the reciprocal, okay? Now you are looking for things that you can slash away. So I see a common factor of 2 here and a common factor of x here. So it might be good to kind of like separate those things out, which is what I've done in a subsequent step. So technically when you're multiplying two rational expressions, it's customary to explicitly show a single rational expression, which is its result, where you multiply the numerators together and the denominators together. If you are comfortable doing the slashing at this stage without showing this extra step, that's fine by me, just as long as you don't make any errors. If you want to, though, you could expand everything out, and then the slashing becomes super duper satisfying. And here's everything that's left all smushed back together, and that's as simplified as that particular example will get. All right, moving on. Here's another one there, and we're going to start by doing the keep, flip, change. Keep the first rational expression the way it is, flip over the second one and change the operation from division to multiplication. Then we want to explicitly show that we're multiplying these things, so, make it one rational expression with raised dots in between the items being multiplied. Factor and prime factorize, if that's even a phrase. Perform the prime factorization of any kind of numerical values that you can, so that all of the slashing can be very straightforward and satisfying at this stage. And go ahead and start slashing. We're going to slash away one factor of x minus 4, one factor of 2, and then keep everything else. The x minus 4 in the numerator, you could drop the parentheses, and the 2 remaining factors of 3 in the denominator, call it a 9, so that it's as concisely represented as possible. All right, cool. That's that one. Moving on. All right, keep, flip, change. Show the multiplication. Factor, 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 as much as you possibly can. Look for common binomial factors and other numerical factors everywhere that you can. Slash, slash, and report everything that is left. And that's it for that one. I very much quickly breezed through that. I hope that's okay. Pause along the way to catch up with the writing of these things whenever you need to. The beauty of YouTube video lectures. Okay, and that's it for that one. Cool, moving on. Keep, flip, change. Multiply numerators to numerators, denominators to denominators. Factor everything that you can. So I'm going to take a little sidebar step in order to factor this second degree trinomial in the numerator. And here's my initializing my diamond. Here is me finishing the diamond, splitting the middle term, factor by grouping, and we're done. So this is the factored form of my second degree trinomial in the numerator space. Otherwise, you have a GCF here you can take out, a GCF here you can take out. You can do the prime factorization of 21, unfold all of that business, and then slash away. And what do you notice happens with this one? This is a very fun and satisfying slashing situation, because look, x minus 2 gone, 3x minus 4 out of here, factor of 3, boom, the 7 as well, everything canceled out. So we have a final answer value of simply a 1 for this particular one. I don't know about you, but it certainly wasn't clear to me when we started this example that it was going to all settle down to just a 1, but there you have it. So fun. A little bit of a mystery unfolding right before our eyes. All right, next example. Oh, actually, we're going to switch gears. I just realized by clicking forward here that we're going to add and subtract some rational expressions. First, we're going to do the version of it that's relatively easy when the denominators are already matching, because then you just add the numerator stuff together, combining like terms, or if you're subtracting, you'll subtract them, in which case you need to, for this version of it, negate or change the sign and operation of every term inside of the Q polynomial, then combine like terms and see if anything else needs to be simplified after that, by virtue of possibly needing to factor and cancel out common factors. Cool. So let's have some examples, and we're going to start off real super easy, relatively easy anyway, in which the denominators match. So recognize that for example A here, having both the denominators of these rational expressions be the same, 3y, you could simply add the numerators together. So you'll have 8 plus x as the numerator for the common denominator, 3y. Then you'll just combine like terms. You'll check to see if there are any common factors in numerator and denominator after you combine like terms. Certainly that's the case here. There's a common factor of 3 that gets divided out. So notice that I didn't bother with writing the prime factorization of 9, which you could do in a subsequent step if you want to. Otherwise, I think it's simple enough for us to divide out the common factor of 3 and report what's left. That's going to be your final answer, 3x over y. Okay, great. Moving on to the next one. Still, the denominators are common for this next example, so we're simply going to subtract the numerator values. And look what we get for this particular one. The numerator and denominator values are the same binomial factor. They can get slashed away, and we'll have an ultimate final answer value of 1 for this particular example. Okay. On to the next. Denominators still match. So go ahead and perform the subtraction over the common denominator of x plus 2, but make sure that you are careful to have that subtraction symbol go in front of the quantity of the polynomial in the numerator of what we would call the subtrahend rational expression. Subtrahend, again, I've used this term in lecture videos in the past and might say it from time to time during the class session. It's just the technical term for the thing being subtracted off in a subtraction problem. So subtrahend is the term for the item being subtracted off. The item that you're subtracting from, the first thing that as you read from left to right in a subtraction problem is called the minuend. So fun little bit of terminology there. Let's go ahead and distribute through this negative sign in order to subtract that polynomial. Now we're ready to combine like terms. We want to see if the resulting numerator, since it's a second degree trinomial, is factorable. So let's go ahead and bust out a diamond, okay, and factor by grouping. So, okay, it's factorable, and we want to replace it with that second degree trinomial and check, can we cancel out any common factors? Yes, I'm really glad that we did go through the trouble of factoring that numerator second degree trinomial, because we have a binomial factor of x plus 2 that can cancel out, and we're left with simply an 2x minus 3. Drop those parentheses because they're not doing anything for you. Great. That's that. That's example C. So what you're seeing now is the black screen, which is just telling me that we are, that we're done with that part of the PowerPoint, but there's more. Here we go. We're going to pick up where we left off on this next PowerPoint. So your lecture notes continue with us. Now we're going to be diving into examples of adding and subtracting rational expressions when the denominators don't match. And so when this happens, you're going to have to find the LCD in order to make a match so you can actually perform the addition or subtraction that you're being tasked with, okay? So let's remind ourselves of the process of finding the LCD. You're going to factor each denominator completely, and the LCD is going to be the product of all unique factors, each raised to the greatest power that appears among all the denominators. So let's have a little bit of practice just finding the LCD of a pair of terms. So let's start numerical. If your denominators are 9 and 15, right, you want to look at the prime factorization of each one, find the highest collection of each distinct factor, which in this case for the 3's, the highest collection of 3's is going to be, there's 2 factors of 3 here, so grab those. There's also a distinct factor of 5 there. Their product is going to be the LCD, which in this case will be 45. So if you were trying to add these two fractions together, you would need to build them up so that their denominators are 45, which you do by, multiplying them by fun ones, which are fractions whose value is 1 but has a fun representation. So examples of fun ones are 5 over 5, 2 over 2, 8 over 8, a million over a million. Anything over itself, right, is a fun one. So you would, in this case, because you want the denominator to turn into a 45, you got to multiply that 9 by a 5. So it would be 5 over 5 would be the fun one you would multiply the 2 9ths by. And then the missing factor for the 15 would be a 3. So the fun one for the 7/15 would be a 3 over 3 if you needed to add or subtract these two fractions. But we're just worried about finding the LCD, which we successfully did for example D. Now let's go ahead and try another example and throw some variables into the mix. Okay, so just focusing on those denominators, go ahead and rewrite 6x to the 3rd power and 8x to the 5th power, where you do the prime factorization of each numerical component for those exponential expressions. And so you're going to consider all the distinct factors you have. You have 2's, you have 3's, and you have x's. So for the 2's, where's the largest collection of 2's? It's the 2 to the 3rd power, right? So grab that. The 3's, who's got the 3's? Well, there's only one 3 present, so we're going to grab it. And then for the x's, who's got the largest collection of x factors? Well, there's only 3 here, but there's 5 there. So grab that 5 collection of x factors, take all the 3 things that I've circled here, multiply them together, and that gets you your LCD. Okay, so you'll have 24x to the 5th power would be the LCD for these two fractions. Okay, Now, let's do another one with some binomial factors for fractions. So these denominators cannot be factored. I'm talking about the a plus 5, a minus 5. They're already as simplified as they can get, and they're distinct binomial factors. So that means that their LCD is just going to be their product. Simple as that. Don't FOIL them out or do anything crazy like that. Leave them in their factored form. That's the way you're going to want to use them when you actually have to add or subtract some rational expressions that have those binomial factors as their denominators. Okay, now one more, or I'm not sure how many examples we have here. I'm not actually looking at the lecture notes. So here's another one. And notice, again, these denominators cannot be factored, the y and the y minus 3. That's as simplified as they get. And they are, again, distinct binomial, or distinct factors. One of them's a binomial, the other one's a monomial. So just multiply them together to get their LCDs, okay? Let's have a little more complicated example here. So this first denominator is already factored as much as it can be factored. And then the 3x minus 12 denominator, that one can be factored by pulling out a factor of 3. So the distinct factors that we see among these two denominators here are, we have some factors of the binomial x minus 4. There's 2 of them here, 1 of them there. And then we also have a distinct factor of 3. So you have to consider all of those. So which factorization has the most iterations of the binomial factor x minus 4? Well, it's the squared one right here. So grab those 2 factors of x minus 4. Then the other distinct factor, that's the 3. Multiply those together, that gives you your LCD. And resist the urge to expand this out by performing the square of the binomial. Just leave it the way it is. You want these things to be in factored form when you are considering next steps in adding or subtracting rational expressions that do not have common denominators, which I believe we're going to get into maybe after this example. Let's try this one more time, just focusing on the denominators. Factor those 2 trinomial second degree polynomials out, right? So here's the factorization of the leftmost rational expression. Here's the factorization of the right. So notice that we have a common binomial factor. So, and it's a tie as far as like who has the most. So when it's a tie, you just, pick one. Oh, sorry, but there's an x plus 3 factor that I'm circling first. That's a distinct factor. You need to grab all distinct factors. And if there's a tie, you just grab one of them, okay? So I went ahead and just grabbed one factor of y minus 1 because this other factorization had just as many. So I do not grab both of them. I know that might feel a little counterintuitive, but believe me, you just want to take the one. And then take the product of all the distinct binomial factors and the one repeat and multiply them all together to get your LCD. Okay, cool. Moving on. Let's actually do some adding and subtracting of rational expressions when they do not have like denominators. By reviewing the procedure first, we're going to do step 1 will be find the LCD of the rational expressions. Step 2 will be rewriting each rational expression as an equivalent expression whose denominator is the LCD, so we need to determine what the fun one will be for each term. And then, of course, do the addition or subtraction, right? And writing the result over the common denominator, and then you want to simplify if you can after that, which may involve more factoring, okay? Cool. Let's bust out several examples, and then after this, I believe we're going to solve some rational equations, and then we'll be done. Like I promised at the beginning of this lecture video, this is going to be a long one, lots of examples. But here we go. We're in the second to the last set of examples with this. Let's start by figuring out what the LCD is for this subtraction of rational expressions example. It looks like the LCD is going to be 15 here. It's numerical, so it's relatively simple, and when one of the denominators is a factor of the other one, like we have here, then the larger of the two is going to be the LCD. So yeah, I'm writing off to the side that the LCD is 15, and I'm going to rewrite the expression with a fun one thrown in the mix to build up the one rational expression that needs to be modified in order to capture the LCD. Notice that there's no fun one for the second rational expression that's being subtracted off because that denominator is already the least common denominator, okay? We're going to perform that multiplication, incorporating the fun one. Now the denominators match. Go ahead and perform the subtraction of the two numerators over the common denominator. And, oh, what did we get here? That's weird, but look what happened in the previous step. 3y minus 3y. Anything minus itself is going to result in 0. A fraction whose numerator value is 0 is 0. Okay, so that's going to be your final answer for that one. Crazy, right? And think about it this way. I mean, if you were looking at this maybe a little bit more objectively, you would probably, without this process, just reduce that rational expression, like simplify it and then subtract. That's another way that you could have tackled this. But I did want to illustrate the whole let's incorporate a fun one version. It's a little bit more lengthy than this alternative that I'm just kind of verbally describing. Both are correct. And whichever way you see to do first is the most correct one. So that's a very much subjective. Great. All right, moving on. Next example, we're going to find the LCD. And so the LCD is going to be what's the least common multiple of 8x and 10x squared. So you need x squared definitely to happen. And then the numerical LCD between 8 and 10, if I'm not mistaken, is 40. So I'm going to say that the LCD is 40x squared. Let's go ahead and rewrite the rational expression, the addition of the rational expressions with appropriate fun ones. So you have to look at each individual denominator, compare it to the LCD, and say to yourself, well, what factors are missing? When comparing the 8x to the 40x squared, it's missing factors of 5 and x. So that's what fueled the choice for making the fun one this 5x over 5x in order to build up the 5 over 8x in order to capture that LCD, okay? Similarly but distinct, the 10x squared denominator that we see over here, in comparing it to the LCD of 40x squared, it's missing a factor of 4. So that's why the LCD, or the fun one over here is a 4 over 4. Multiply, add, and then simplify if possible. So is there any kind of a, can we factor anything meaningful out of the numerator? I don't think so. So it looks like that's as factored as, or as simplified as it's going to get. It might look like there's more to do on this one just because the numbers are relatively large, but look very critically at it and recognize, hey, there is nothing to do. That numerator binomial has a GCF of 1. So we're good to go to move on to the next example. And here it is. All right, much more interesting denominators going on here. It looks like the LCD is going to be x plus 3 times x minus 3. Basically the denominator, the factored form of the denominator in the minuend rational expression. So and how do I know that? Because I factored this denominator and I recognize that this other denominator, the subtrahend denominator, is going to be a factor that's already captured in the minuend denominator. So there you go. So that's what is fueling my my conclusion that the LCD is as follows. And remember, you want your LCD when ever possible to remain in factored form. Keep it in factored form for as long as possible, and even up until the final answer too. Your final answer should be all the way factored. Yeah, just as a convention. So go ahead and take your fun one of x minus 3 over x minus 3 for the subtrahend. That's the rational expression that's being subtracted off. Multiply, subtract. So when you subtract over the common denominator, take the subtraction symbol and put it in front of the 5, right? So that you remember or recognize that you need to distribute through a factor of -5 in order to further simplify that numerator. And that's what we're going to do right here. Then we have an instance in which we need to combine like terms, the x terms here between the 10x and the 5x. Go ahead and perform that subtraction. Now it's time to assess. Can I simplify any further? Well, sure. This numerator has a GCF of 5, so go ahead and pull that out. Haha! Recognize at this stage that we have a common factor of x plus 3, so slash those away and report what is left. And that's it for that one. I mean, there was kind of a lot of work involved, certainly, and it gets more complicated than this, but there you have it. That's what we would get for this one. It can't be simplified any further. All right, moving on to the next example. We have a LCD of, it looks like 7x times the quantity x plus 1. You just take those are distinct factors. One's binomial and one's a monomial, and you just multiply them together, but keep them factored, keep the factors separated. And then compare that LCD to your denominators to determine what an appropriate fun one will be for each of them, if needed. And multiply and add and distribute that 5. Combine like terms. Simplify further if necessary. Can that numerator be factored? It cannot. 19x plus 5 has a trivial GCF of 1. So this is the extent of the work that we need to show. There's nothing else that you can do to simplify. So this 19x plus 5 all over 7x plus the quantity x plus 1, that's your final answer. All right, moving on to the next example. Oh, this one's an interesting one because it looks like we're just, that first term is an irrational expression. You could argue that it is, though. You could just kind of call it a 2 over 1 here and say to yourself, well, the LCD has got to be the one, denominator that we have, the non-trivial one, this denominator here being the trivial one. So hopefully that makes it abundantly clear that our fun one for the item that's the whole number that we're now turning into a fraction is going to be this x plus 5 over x plus 5. Go ahead and multiply. Now you can add, distribute that 2 in the numerator, combine like terms. Check. Can you factor the numerator? Can you simplify this any further? No, you cannot. So that is the end of this example. There's nothing else you can do for this one. It's all the way simplified. Cool. Moving on. All right, now it's going to get a little bit more complicated because these denominators are getting a little more intense. All right, so what we need to do is probably factor each of those denominators, right? And if you do, so sorry, I kind of gave it away a little bit, you're going to find that your LCD is 4x times the quantity 3x plus 2. So yeah, if you take out, if you factor both of these, you'll have this one is going to be x times the quantity 3x plus 2. This one's going to be 4 times the quantity 3x plus 2. So you take all of those distinct factors and you multiply them together, and that's what gives you your LCD. So once we move forward in the rest of this problem, it is advantageous to us to work with these denominators in factored form. So this is what I mean. Take that 3x squared plus 2x and work with it in its factored form from now on. That'll make it easier to determine what the fun one should be as far as its multiplier is concerned, because you're looking at x times the quantity 3x plus 2, comparing it to the LCD, and you're like, oh, it's missing a factor of 4. That's why the fun one is a 4 over 4 here. Similarly but distinct, this factorization is missing a factor of x with comparison to the LCD. So the fun one here will be an x over x. Great. Go ahead and multiply. Subtract. Maybe rearrange this or not. I forget what I do. Here, let's go ahead. Oh, actually, I don't bother with rearranging this. Leaving this as your final answer is perfectly acceptable. That numerator, it might look like it's a difference of squares situation, but this coefficient in front of the squared term makes it not difference of squares. It kind of ruins it for it. So this numerator binomial cannot be factored any further. So it's prime. You can't cancel it with anything that's down here. So you're going to call this done. Box it up, call it a day. Moving on to the next example, H here. All right, factor those denominators, figure out the LCD, and you're going to find that the LCD is x plus 2, x plus 2, x minus 2. Or you can call it x plus 2 quantity squared, but I think it's better to leave it expanded. So yeah, I don't know. Personally, I like that better as far as like the rest of the process is concerned when you're busting out your fun ones, I think it's a little easier to see which factors are missing when they're all expanded out, avoiding the exponential notation. So here is the rewriting of the original problem with factored denominators and corresponding fun ones, okay? Now you multiply, you add, you distribute, combine like terms, see if you can factor that numerator. We can. You can factor out a factor of x. It doesn't allow you to slash anything away in the next step, but at least you checked to see if it could, right? You always want to leave both numerator and denominator as factored as possible. And I did a thing here which kind of flies in the face of what I was saying earlier about keeping these things expanded in the earlier part of the process. When you're presenting your final answer, you always want to do so as concisely as possible. So if you have multiple binomial factors, you'll want to scrunch them up into the exponential notation just to display it as, like I said, as concisely as possible. So that's why this final answer is desirable. Okay, cool. Let me know if you have any questions on these when we come back to class. Let's go ahead and, okay, so that was the last example, thank goodness, with adding and subtracting rational expressions that do not share common denominator. Now let's practice solving some rational equations, and then we'll be done with this lecture video, which is already so lengthy as it is. Let's go over the process of solving a rational equation. So a rational equation is an equation that contains at least one rational expression. In order to solve it, we want to multiply both sides of the equation by the LCD. So being able to figure out the LCD is still extremely relevant for this continued part of the process here when we upgrade our endeavors to the world of equations rather than just fiddling around with expressions, okay? And what's the difference between an expression and an equation, you might be wondering at this point, some of you anyway. An expression is a collection of terms or a single term or whatever, but there's no equal sign involved, whereas an equation, it's a collection of terms, items, whatever, that contain an equal sign. So that's literally the difference, okay? So we're going to have an equal sign for these remaining examples. Let's continue talking about the process. Step 2 would be distribute, combine like terms, and solve the resulting equation. So it's a 2-step process, basically. Three-step, excuse me. This is a very important part of it that is easy to overlook. In fact, in thinking about this process, in preparing to talk to you, I have forgotten about step 3, which is super important. You want to look for the domain, it should say violation, or, the numerical values that are not allowed in the rational expression by focusing on what values make the denominators 0, right? Okay, so we'll definitely have that be part of the end of the process of solving our rational equations here. All right, here's our first example. And notice that we're starting off real slow and relatively easy. Notice that there's no variable part in any of these denominators. They're completely numerical. So there won't be any value of x that we would consider excluding in this very first example. But we do want to tackle step 1 and find the LCD. So what's the LCD here? So the denominators are 4, 5, and 20. The largest denominator has as factors both of the other ones. So that means that the LCD here is going to be the 20, the largest one. And so we're going to rewrite the rational equation multiplying both sides of it by 20, or 20 over 1 if you like, okay? It might be nice to put it as a fraction just so that you are lining up numerators to numerators, denominators to denominators, okay? Now we want to distribute this 20 over 1 to both of the rational expressions that are being added inside of those parentheses, okay? Now we're ready to slash. So slash away. This first term has a common factor of 4, so these values that you see in blue next to the slashes, those are the remaining factors after slashing away the greatest common factor. Here the greatest common factor is 5. Here, the greatest common factor is the 20. The 20 slashed out outrightedly on the right-hand side. And then you report everything else that's left over. So this is what I like to call clean house. We got a clean house at this next stage, in which we will have 5x plus 16 equal to 1. Now we have a linear equation of one variable. We could solve that with relative ease. We're going to subtract 16 from both sides. We're going to divide both sides by 5, and we're going to get a final answer of -3. Now, if our denominators in the original rational equation had any variables in them, any instances of x, as is the variable in this case, we want to make sure that a value of -3 is not going to make any of the denominators 0. But since all of our denominators are strictly numerical, it's not something that we need to check here. It's just something to keep in mind with some of these future examples. Speaking of which, let's go ahead and tackle the next one right away. Oh, again, denominators are numerical, so we're going to not worry about checking our answer as the last stage. We don't have to do step 3 as it was originally described. We're just going to do steps 1 and 2. Okay, so again, what's the LCD? It's 15 here for the same reason that the previous examples LCD was 20. Multiply both sides by 15, or rather 15 over 1. Distribute on the left-hand side. Slash away common factors. Boop, boop, boop. Remember, when you're going to perform the multiplications that ensue after the slashing is done, because these numerator values here are binomial factors, you got to put them inside some parentheses. It's a very important step that could easily get overlooked if you're rushing, okay? Then we're going to distribute, combine like terms, and then it's a linear equation in one variable. We know what to do here. Subtract 13 from both sides. Divide both sides by 2, and we'll have x equals -6, which, you know, that solution is completely viable. There's no reason why we would even check its viability, because the original rational equation had no variable parts in the denominators. Cool. Moving on. Now we have an instance in which we definitely need to check our what's it called? To see if our solution is viable, because x cannot equal what? 0, right? Because if we have x equaling 0, then this rational expression is going to be undefined. So we want to make sure that we're not going to get a value of 0 for our final answer. But let's determine what the LCD is first. The LCD is x. We only have one denominator happening, so its value is going to be the LCD. Multiply both sides by x. Distribute through. Now, I opted for not doing the whole x over 1 here because there was only one instance of a fraction, or a rational expression rather, and I felt comfortable just going ahead and doing the slashing that is associated with this. Or nope, that's not true. I went ahead and then the next step I was like, you know what? I want to have it as x over 1. I forgot that I did that. Anyway, so that makes the slashing that occurs in this next step very satisfying because it's nicely set up. Then you report what is left. You're going to see that you have a second-degree polynomial equation. Go ahead and put everything on one side. So essentially from this step to the current step that you're seeing here, I subtracted both sides by 2x and 6 to get this polynomial equation that you see here. Factor the right-hand side, and you'll get this. I didn't bother with the diamond method. Hopefully if you were like, ooh, I see an instance where I need to factor, you might have paused and worked that out. And if not, here you go. I've done the work for you. That's the factored form. Use the zero product principle in order to determine the two solutions of x equals either 1 or -6, and then check. Is it going to be violating any domain restrictions or creating rational expressions that are undefined? It won't. Neither solution creates an undefined value, so they are both viable solutions. You would circle them both or enter both of them in if you did something like this for like the online homework or exam or something like that. Cool. All right. Let's do some more examples. All right. Ooh, this one's markedly more complex, but one thing that's really cool about these examples that you're going to see like in your textbook and homework and exams and stuff like that, is that chances are the second degree trinomial factors out to be exactly the binomials that you otherwise see in these equations. They're made to work out nicely, so keep that in mind. And in fact, the LCD here is x minus 3 times x plus 5, because that is exactly the factorization of this second degree trinomial. Okay, so go ahead and multiply both sides by that LCD, and I'm going to go ahead and rewrite the first rational expression as the factored form for the denominator there. I'm doing that strategically because I want the slashing that's going to happen in a subsequent step to be very satisfying. And even though I might write it this way initially, you could go straight to this setup, and that's what I would recommend. Throw that LCD that you're multiplying on both sides over a 1, so it's very easy to tell who's in the numerator space and who's in the denominator space. Distribute through. This is where it's going to get kind of complicated because you have a lot of, details in distributing through these two binomials, right? So writing relatively small and being very organized and using your best possible handwriting is definitely in your purview here at this stage. But what's cool is we have set ourselves up nicely to do some very satisfying slashing. Bing, bang, boom, those slash away, these slash away, and then you're just going to report what's left over. And what's really cool about multiplying both sides of the rational equation by the LCD is that after you do the slashing, you are getting a linear equation in one variable with these types of values. So now we just need to distribute, combine like terms, and solve this linear equation. I mean, and because of the structure that we currently have, you can move forward in 4 different ways, and they're all correct. You could either subtract 3x from both sides, add 20 to both sides, add 2x to both sides, or subtract 6 from both sides. Let's see what I decided to do. It looks like I decided to add 2x to both sides. Then the next logical step, the most efficient step, would be adding 20 to both sides, dividing both sides by 5, and we're good. I mean, that's going to be the solution that I calculate. Now, double check. Does this violate any of the domain restrictions? Well, check back with the LCD. When would the LCD be equal to 0? That's what you want to be looking for, because that captures all possibilities of 0 events in all of the denominators, right? So the LCD would be 0 when x equals 3 or negative 5. Is 26 over 5 equal to 3 or negative 5? No. So no undefined values, the solution is viable. Okay, so you would keep it and you would move on to the next problem, which is this fun one right here. All right, so the LCD here is x minus 1. We're going to multiply both sides by x minus 1, or, x minus 1 over 1. If you want to skip this first step, like in writing, how you write this down, and just go for the second step, by all means do so. Like, I totally see how that would be good. Or just, write it this way, but then throw it over a 1. You don't necessarily have to rewrite it like I do here. It just was easier than because I just retyped it. And anyway, for the purposes of making this PowerPoint, it was easier. Okay, distribute, and then, you only need to distribute on the left-hand side. On the right-hand side. The left-hand side, I just dropped the parentheses. Do some slashing everywhere that you can. And then the resulting bit will be a linear equation in one variable. Distribute through this 3 right here. Combine like terms. And you get a solution of x equals 1. But wait a second. What happens if I check in with the LCD? When is the LCD going to be 0? Well, it's 0 when x equals 1. But that's the solution that I calculated. So what do I do in this case? Right? You got to check it, and if you find a violation, you're going to just say that, well, the solution that I calculated here is, it's extraneous, so therefore there's no solution. Yes, you could go through all of the trouble of calculating a solution that doesn't work. It's possible, and here's a case in point. All right? So try not to get too frustrated with it. The endeavor of figuring this out is a valuable bit of practice. All right, let's see what else we have. Oh yeah, and if you have no solution, you could certainly represent that with the symbol, the empty set symbol of a 0 with a slash through it. Okay, let's do another example here. The LCD is relatively simple because the denominators that are present are both the same. So we're going to multiply both sides by that LCD, distribute through. I opted for not doing the over 1 necessarily for this initial step because there's just as many instances of needing it versus not needing it. So when I distribute it through, I just distribute it for explicitly as an x plus 3 factor for the first term in the distribution on the left-hand side, but then I gave it a fraction representation for distributing over the second term. And I did that because the second term was the rational expression. And then I did a similar thing on the right-hand side of the equation. And now we're ready to slash, clean house, distribute, combine like terms, factor that second degree trinomial, and determine the solution set using the zero product principle, either x equals -3 or x equals 4, right? Because those are the instances in which these binomials could take on a value of 0 and then being multiplied. One of the factors has to be 0 in order for the product to be 0. Okay, now check your solutions for viability. We have two. Do they both work? It looks like one of these creates an undefined value for a couple of these rational expressions, right? It's the -3 one, because check back with the LCD. When is the LCD equal to 0? Well, it's equal to 0 when x equals -3. So that means this guy right over here is deemed extraneous. We cross it out. We don't include it as the part of the solution set, and but the other calculated solution of x equals 4 is viable, so that becomes the only solution here. Okay. Whew. And I believe on that note, we are done with this lecture video. Thank you so much for your attention. I look forward to seeing you again in class, and just have a lovely day.